So, welcome everybody. The next talk is under the topic shoplifting, shopshifting, sorry. Shoplifting is something completely different. It has nothing to do with shopshifting. The outcome is the same. And I present to you Carsten Nohl, Fabian Bräunlein, and Dexter from Berlin. And some of you may have already seen the one or the other face here. And you may have heard of things like the MyFair RFID problems that we had, the GSM SIM card hacks, and things like bad USB. And these people and people around them are all responsible for that. So give them a warm applause, and stage is yours.
Thank you very much. It's great to be back, looking at yet another technology and searching for security vulnerabilities. We focus our research on technologies that most of us use on a daily basis, that are typically outdated, very widely deployed, and insecure. It took us many years to finally come around to look at payment protocols, which we'll be discussing today. In parts, it took so long because we just didn't think we would find anything. After all, some of the best people in our industry work at banks, and banks have among the most developed risk management. So at least in my experience, banks are good at reacting to security evolution. That's what I thought up until maybe the middle of this year when we started this research. And we're here now today to take this preconception away from whoever may still be suffering from this illusion that banks actually do keep their systems very secure. At least we found in two cases, two very widely deployed protocols that there's gaping holes and have been for a couple of years. Both of these protocols are involved in payment. That is, if you go into a store and you pay with a card, those protocols are invoked, at least in Germany. And the protocols are called ZVT and Poseidon. They're used for very different purposes, but they both terminate at a payment terminal. The one protocol, ZVT, is spoken between a cashier station and this payment terminal. So somebody would scan some items or type in some amounts into this cashier station and then say, now please pay. And a command is sent to the payment terminal, which then requests a card and perhaps a PIN number for most transactions in Germany. And then in turn it invokes another protocol that this payment terminal speaks with a payment processor. It's a service provider that connects these terminals to banks and basically facilitates the actual payment. And then the payment processor or the bank, they validate the account details and so forth. They send a confirmation, and that confirmation, again, over ZVT, is sent back to the cashier station. That is, in a nutshell, how a payment transaction works. So it's based on two protocols, both of them fairly old, and probably by virtue of being so old, very widely deployed. In Germany, you will hardly find anything other than these two protocols being used. We'll look at an international angle towards the end of the talk. Just a short summary, most of these problems would probably exist in most other countries as well. So let's, in turn, look at ZVT and then Poseidon to identify their security issues. Starting with ZVT. This is, again, the protocol that's spoken in the shop between a cashier station and a terminal, but in almost all cases, over a network connection. Very old systems would use a serial cable, but today a network is used. So assuming that a fraudster somehow can get access to that local network by plugging into some open ports or by even being a customer at your hotel and just being connected to the same Wi-Fi as your cashier system, what can this attacker do? Let's start with something simple that doesn't even really require any hacking. In this case, somebody wants to steal the magnetic stripe details of a card. So the way this should work is the cashier station sends a command to the payment terminal and then gets a confirmation back after some processing. Now, what the attacker does in this case is get in between those two in a connection through just traditional ARP spoofing. So you proxy the connection between the cashier station and the payment terminal sitting in the local network again. We'll look at internet-wide attacks in a few minutes, but for now, we're talking about inside the shop or in Wi-Fi range of that shop, right? So you ARP spoof, and you receive that authorization request that's supposed to be sent to the payment terminal, where the cashier station basically says, there's a customer here, the customer wants to pay something, please authorize the payment, right? We take that command and do not forward it, but instead send another command, which basically says, read a card. So the terminal will then display what the customer expects. Please insert a card. Customer does so, and the magnetic stripe information is read and sent back over the network to the attacker. No transaction has been done yet. Immediately following these magnetic stripe details, the attacker would then send an actual authorization request message supplying the magnetic stripe info. So instead of asking for a card, the payment terminal just takes this mag stripe now and goes through the transaction. So two things happen. First, the attacker did receive a copy of the mag stripe. Second, the actual transaction, the intended transaction, did go through. So neither the customer nor the merchant sees any different. But the attacker does have a copy of the mag stripe now. And in countries where mag stripe is enough, let's say US, prior to chip and PIN, this is enough to completely clone a card. Fortunately, most other countries do require PIN numbers, making this attack ineffective. But perhaps motivating a slightly improved attack. So let's say the fraudster wanted to also steal the PIN number remotely, right? Mag stripe and PIN number, that's really all you need to pay in Germany, say. So the way PIN transactions are supposed to work, they are much more secured, or well, they're secured at all versus mag stripe, which isn't secured. So the top part of this slide shows how a PIN transaction is supposed to work. Again, over ZVT, the cashier desk or whatever speaking to the terminal in the store sends an authorization request, this time specifically saying, do require a PIN number. Or perhaps that is even configured in the terminal to always require a PIN number. Either way, inside the terminal, all the security magic happens now. There's different components of the terminal. There's a main CPU that does all the network communication, both ZVT and Poseidon, which is supposed to be somewhat secure, but really isn't. As, by the way, some research a couple of years has shown that specifically looked at the security of one of these terminals. But that's not the topic of today. We're looking at the standard security. But so inside this terminal, there's also a hardware security module, an HSM. And that HSM does all the heavy lifting when it comes to cryptographic keys and so forth. The HSM is also directly connected to the display and the pin pad of the machine. So you tell the HSM inside the terminal, do a PIN transaction. It shows something on the display, enter PIN. It receives the input. And instead of giving out the PIN number to the less secure side of the terminal, it encrypts it with a key that only the payment processor is supposed to have. So the main CPU or anybody really outside of the HSM does not see the PIN number. That's how things are supposed to work. Now, the lower part of the slide develops an attack idea with one catch. We'll resolve that in a minute, though. This attack idea would use a different message to actually receive the PIN number. So instead of saying, do a PIN transaction, it would just say, display some text and give me the input. That would work beautifully, right? So you display the text, give me the PIN number, and whatever's typed in, you get that input. This very flexible functionality, we don't really know what it's ever used for. We've never seen it, but we're suspecting it's used for things like asking customers for their zip code or something, right? Type something in and send it over the network. And we've partly never seen this because it really can't be used. These messages need to be signed. We don't know who's supposed to sign these messages. We've tried to find a person, but nobody feels responsible. So there's some functionality in the standard here that's never used, and nobody knows how to use it. Because of this cryptographic signature, on this slide called a message authentication code, MAC, that's required, and it's actually checked by the HSM. So if you want to do your please enter zip code scheme across all your stores, you got to get your message signed, and that signed message then works across all terminals. And if we want our please enter PIN number message to be shown, we got to get this signed or find some way to sign this ourselves. And now we're entering the real hacking, so I'm handing over to Fabian, who did almost all this research. So it was just my honor to introduce these two guys here. Thank you.
All right, so to find valid MACs for arbitrary texts, we exploited a time-based side channel vulnerability within one HSM implementation. So for this to work reliable, we had to have the ability to send messages directly to the HSM. To accomplish that, we used an active JTAG interface we found for the main CPU on the PCB and loaded our custom assembly program. What this one did was just sending messages with our text and some MACs to the HSM and stop the time that it needs to respond. So we are doing that and are trying every single possibility, every single value for the first byte of this 8-byte MAC. When you do that, you will see that, so that's a bit oversimplified, but you will get the gist. You will see that for one particular value, the HSM needs a bit longer to respond, so like just 5 CPU cycles within the HSM. Now you already have the first digit, the first byte of this 8-byte MAC. You can set this and do the same thing for the second one. So why does that work? This works because they use a symmetric key for the calculation of the MAC within the HSM. There is a key that the payment processor has and that is stored inside the HSM, which is able to calculate the correct MAC for any text. What happens next? So this is the first minor issue because you should use asymmetric cryptography. The next thing is that the comparison between the correct MAC that has been calculated within the HSM and the MAC we have input through this display text message is compared byte by byte. So it checks if the first byte of the input message matches the first byte of the correct MAC, and if it doesn't match, it will return immediately. If it matches, it will try to compare the second byte, and if it doesn't match, it will return immediately. So this time it needs to check one more byte we can measure with some more work. So with this thing, with the correct MAC for the please enter PIN screen, we can give you a quick demonstration of how this works in real life. And for that, we would need the GoPro that we already have. Big GoPro, yeah. So this is the setup here. Here we need the computer with the green text on the black terminal. All right. Here we have a normal cashier register. It's some Windows XP software running. Here we have the actual payment terminal. These two are connected through this Fritzbox standing here, just some normal internal home network. Now, there's also another participant in the setup, which is the attacker. In this case, connected via LAN, but he could also be connected via Wi-Fi in the car, outside the street, and so on. So what we have running here is the attacker software. When we will initiate a payment through this cashier register, the attacker, as a man in the middle between these two devices, will simply drop this message and replace it with the first read card message. We will pay with the card. Yeah. All right. Please insert the card. Now, yeah. Here, we can already see the card data, partially censored for our own safety. And he has entered the PIN already, so what you have seen, it was a bit fast, but what you have seen was the PIN he has entered appeared here as soon as he entered it, because it wasn't the real PIN entry screen. It was just our fake PIN entry screen. I hope you have seen that, you saw that on the terminal. That's the first demo. That's how we steal the PIN number. So, 1 2 demo.
If I remember correctly, your receipt, though, gives out the attack a little bit, right? Can we show this receipt? GoPro, while you're here. So this line in a normal transaction, when you enter a PIN number, is supposed to say Girocard, and instead this now says ELV offline. So in some cases, it's actually apparent, but who actually pays attention to these details, right?
Right. In addition to this, means that the transaction has gone through with Lastschrift, without the PIN. However, we can also choose our attack to simply fail the first time, so it says like system failure or PIN incorrect, and we'll do a second transaction again with PIN authorization, that's fine. Or in bigger setups, not the terminal itself prints the receipt, but an external printer that's connected to the cashier register. And for that to work, the terminal, again, has to send the receipt line by line to the cashier register, again, without any encryption or authentication, so we can simply replace the line with Girocard or drop some lines and do whatever you want.
Mm-hmm. Very cool. So that was an attack against the customer. That is pretty much everybody here, unless you really only ever pay with cash. There's some other attacks that target the merchant instead, so everybody who operates one of these terminals. And according to the banks, there's 770,000 such terminals in operation today in Germany. So I guess at this point in time, everybody who has even the tiniest of shops will accept cashless payment. So let's look at that next.
So for the next attack, we are trying to get all the money that's been transferred on this terminal to our own bank account. Again, we assume we have local access to the network, but this time we won't try to become man in the middle between the cashier register and the terminal, but between the terminal and the internet. In this case, the payment processor. By ARP spoofing again. So that VT includes a message and defines this message in the specification to reset the terminal ID, which is basically the identifier that says to which bank account the terminal is linked to. We can reset and set this again with a password. More on that we will show later. If we have set this, we will now tell the terminal to initiate an extended diagnose to the backend again. So we tell it via the ZVT protocol to initiate a message on the Poseidon protocol. We need that because when we reset the terminal ID, the terminal will get reconfigured for the attacker terminal ID, so for my one. And this also means that the merchant banner, so in German it's the Händler logo, the thing that's printed on the top of every receipt, this would also be my one, the attacker's one, but we don't want that. So we tell the terminal to make another transaction, another extended diagnose. We will simply pass that through to the backend as a man in the middle, and the response includes some limits for offline electronic cash and so on, and also the merchant banner. And this, again, we can simply swap. We can swap with the original one, so no one will get that this idea actually occurred. And this is, again, possible because no authentication is implemented here. Now for the actual transaction. If the backend port is already the correct one, we can simply pass all the messages through. So the backend port is, each payment processor has like one IP address responding for all the terminals. However, for load balancing reasons or something like that, they have like 100 different ports, each port responsible for 50,000 terminals, but each terminal can only be managed by one specific port. So if this port already matches, we can simply pass them through. Every payment done by this terminal will now result in some more money in our bank account. If this one doesn't match, we as a man in the middle can simply redirect the messages to the correct backend parameters. And again, let's see it in action. So what we have here is a terminal. We have configured it to be configured as another merchant. You will see in the end which one it was. Again, we have the attacker's PC that's running the malicious software. And Now we will issue the registration, just that we are able to send ZVT messages to the terminal. And now we will reset the terminal ID from the one that's correctly set to our own one, the one we have got from our contract with the payment processor. We are setting this terminal ID. And now the terminal already gets its new configuration. Encrypted, as you will see, but it received that.
So this is all happening with real terminals or for real transactions. So whoever is watching this at the banks, thank you for not blocking us yet.
But we use the 3G network, so in case they have blocked the IP address range here. Oh, right. So normally, this thing, you recognize it, this would have been printed on the terminal itself. We can see now, this terminal now prints as belonging to SR Labs. Normally, this would be the full terminal ID that we censored a bit. And you can see this is the whole configuration, and it's also configured to be able to issue prepaid cards. Normally, this would be printed on the terminal, but because that would be pretty uncool, because then you would recognize it, we transferred all the output to our own, to our notebook. Now we will start the man-in-the-middle server. For this last part, exchanging the terminal banner, we will change the logo, and we will now issue a demo transaction. So just like the cashier register software did, we will now issue a transaction. And as you will see, this terminal now belongs to, or still belongs to, can you see that?
Put it on the table, yeah.
Sorry.
Can we switch back to the slides? Thank you. So that's how you steal money from an actual merchant while in the store. That would perhaps be the first catch, that you have to be in the store. The second catch, as probably the ones following along noted, is the attacker also needs to be merchant here. You just change from money going to one merchant account, from that to going to another merchant account, but you need to be registered as a merchant somehow, right? There may be a cache. I don't know how well set up criminals are with actual businesses, but the next attack we're going to show does not come with this cache. It does not require you to be in the store and does not require you to have anything pre-configured. And this is an attack on the Poseidon protocol. Remember, that's the protocol spoken between the terminal and the payment processor, right? Take it away.
All right, so now for the third attack. In that case, what we are taking a specific look at is the initialization routine of Poseidon. This part is normally done at the payment processor when you get your terminal pre-configured. Here's done this configuration to assign your terminal to your bank account to make this match. How is this done? The terminal sends a Poseidon initialization routine with a terminal ID to the backend. The backend then will get the configuration for that terminal ID, send it to the payment terminal in an encrypted way, symmetrically encrypted with a key only within the HSM and the payment processor has. So far, so good. That's the normal pre-shared key thing that we know. However, what we have found is that this key, this exact same key, is used not in only one terminal, but in many, many terminals. So what is left of this authentication is just a username, the terminal ID. And this username is public, as you will see. So the idea now is to have our own terminal that we got from eBay. We got like 3 of them for €7, including shipping costs. And configure our terminal to act like just some random terminal somewhere, for example, in Bonn, the mouse shop, as we have demonstrated. And at that point, I almost feel like apologizing, because for this hack, no actual hacking is involved. It's just, the system is just broken in that case. You will see. So you just need a few parameters to configure your terminal as another one. And this is, at first, the service management password only service technicians should have. The second one is the terminal ID of your victim. And the last one is the backend port that is responsible for managing your victim's terminal ID. So the first one, how do we get that? You will simply Google and find it on the internet in some internal documents. This one is the same across all terminals of one payment processor, so completely independent of the model. Every terminal you got from the same payment processor, the same password. So the second one, the terminal ID. As you have already seen, you can find it on every receipt, and you can guess them as they are assigned incrementally. Second one. And for the last one, there are like 100 different possibilities, so just try them all and see which one of these 100 ports doesn't answer with a message saying, I don't know you, but with a merchant banner. So we have all 3 things set. Let's demonstrate it. So for this demonstration, we have already told you we don't have to be on the same network. So this is the terminal here for CCC that we have shown you. We will simply disconnect that. It's not on the same network. What we have here is a terminal without any terminal ID. We just set that into factory reset. This is how you would get it from eBay if the seller did a good job and put it in factory reset. All right, the service password.
Nein, ihr blockiert das gerade.
Okay. Okay, yeah, no camera is good. Good.
Komm, zeig's doch.
All right. We have entered the terminal ID. The backend port is already correct.
Diagnose.
And we will issue an extended diagnose to get the new configuration.
And once you're registered, once you're registered here, what can you actually do to that victim merchant?
We will show the prepaid top-up. So if the victim merchant has the prepaid prepaid feature activated, we will have it activated as well, because we are the victim's terminal. So what we can do is simply print prepaid top-ups, and, for example, call our own premium number to make it to actual money or try to sell it.
Well, let's try that.
So let's try that. Some O2 maybe, 15 euros is enough. Of course, we paid in cash.
Does anybody actually use O2 prepaid? No? Well,
Yeah.
I'm sure somebody will find this useful.
It's open.
Okay.
We will also shortly demonstrate the second way to get money, and this is simply to
show that too? Yeah.
transfer ourselves some money.
So there's a feature called refund, but it is completely independent from previous transactions. So a refund is a transaction with a negative value, and you can do this to any bank account.
So, 100? Yeah, 100 sounds good. Ach.
Can we go back to the slides? All right, that was pretty fast. So let's summarize what just happened. Somewhere in Germany, there's a terminal configured with a certain terminal ID, and that terminal ID says this terminal belongs to a certain merchant. So every money that's put into that terminal goes to that merchant account, and everything that's paid with that terminal comes out from that account. Now here's a second terminal, and we configure that second terminal to the same terminal ID. And it goes through a cryptographic process by which it registers itself with the backend. This leaves the original terminal completely working, so the merchant can still do in their shop whatever they want, but it's a second terminal, a complete clone of the first one that now can do the exact same things. If we were to send money into that terminal, the merchant would get the money, but if we do refunds or SIM card top-up from that terminal, the money comes out from that merchant's account. Right? Very straightforward. You saw what it took, 3 little numbers, all of which are easy to find. Right? Based on a terminal that we purchased on eBay. Now, what's the maximum scale of fraud that somebody could take this towards? First of all, you don't have to do this manual on your terminal. Everything we just did, you can do over ZVT, so you can script this. And it's attractive to script it if you had a long list of valid terminal IDs. Now, I should note that these are assigned incrementally. So if you know one terminal ID, if you know one terminal ID, you know hundreds of thousands of valid terminal IDs. Right? So you register your terminal over ZVT with one merchant at a time, go through a long succession, thousands, tens of thousands, and send refunds or print top-up money from every single account. In Germany, through this Poseidon protocol, probably you can take this to other countries too. Poseidon is just one dialect of a more internationally spoken ISO standard, so chances are this works in other countries as well. So this could really be a pretty large fraud scheme that fortunately hasn't occurred yet, and there's still time to fix it. Again, those people at the banks, right? Summarizing over the 3 attacks we've seen so far. So there's 2 protocols in Germany that are used for payments. Both of them are severely broken, and they affect customers, mostly in the store, by stealing their PIN numbers and MAC stripes. They affect merchants in the store or even over the internet. We've tried this Poseidon attack over Tor, works beautifully. Right? And coincidentally, these protocols, of course, were designed completely independently from one another. They both are vulnerable because of the same root cause. They share secret keys across terminals. We saw in the ZVT case that we needed to sign a message. That signed message was valid across all the different terminals because they all have the same signing key in it. We saw in Poseidon that we could just register one terminal as another one because all of them actually properly authenticate to the backend cryptographically, all of which with the same key though. So they're not distinguishable. It's secure as long as every terminal is in good hands, which of course is a silly assumption in a scheme like that. So each of these protocols is severely broken, and we should have just stopped our research here. But we wanted to get those keys, and Dexter wouldn't be here with us today if there weren't some hardware hacking involved. So we snuck in a few weeks of actual hardware hacking, and Dexter's going to tell you what he did.
Okay, well, yeah, Maker works. Let's go. Let's talk about the HSM. I did with the HSM module with our research. The HSM module is where all the magic happens. So that's the gray box you see on the picture above. That's the HSM module, and it's basically a smart card on steroids. So it has a display directly connected, as said. It has a keypad connected, and it processes all the sensitive data. Of course, you want to have this area, at least in the terminal, well protected. So you want to have that separated from the application processor where all the insecure stuff happens. There are a couple of protection measures. For example, one important characteristic is that the static RAM, the SRAM, that holds the secret keys is battery backed up. So if the battery dies, you lose the keys. And that's just because it's simple to erase a battery backed up SRAM. You just shut down the power. Around the module are a couple of switches, and these switches, if an attacker unscrews the case, then you lift the switches and then you chip the tamper protection. And but that's no problem. That's easy to defeat. There's a more elaborated protection measure as well. So there's a mesh underneath this cap. There's a metallized, a thin metallized mesh that is printed with a conductive ink in the inner surface of the HSM cap. And and if an attacker would drill or cut or even rip off the cap, then you would trip the tamper protection, of course. We found an exploitable mechanical weakness in this particular implementation. We found in our test terminals there. And if you look carefully at the picture, you see on the gray cap, you see in the corners, you see these little dents. That is where the mesh is electrically connected to the underlying PCB. So there it's connected to the circuit inside that continuum monitors the mesh. So this is a continuous monitoring, unlike smart cards where you don't have a continuous monitor. If they're off, but this is always on. And the problem is that the connection is only in the four corners, not at the sides. So at the sides, there is a possibility to enter the HSM, the confined space, with some metallic piece or something. And furthermore, this cap is, during the manufacturing process, this is glued on top of the PCB with a slightly rubbery glue. And this glue leaves a small slot. And we thought of, how can we try to push something under it and properly defeat the tamper protection? And we found something, from the doctors, basically, that's a syringe needle. We flattened that with a pair of pliers. And indeed, we managed to push that under the cap, underneath the mesh, right into the HSM. And we made an experimentation. We found a weak spot. In our case, it was just the power supply of the tamper protection. We need to short out to ground. So then it's defeated, then it's off. And then we can safely open the mesh. You see the grounding clip on the left side. That's the short circuit of the temporal protection detection circuit. And we use the soldering iron to cut it because you want to avoid any vibrations, of course. This is a delicate task. And yeah, then the fruits are exposed. You have physical access to the flash, to the SRAM, to the microcontroller, and even to the JTAG. And in case JTAG doesn't work, and you are only interested in the flash, yeah, there are ways to do it. That's how we did it the first time. And yeah, so here we have attached the JTAG interface to the HSM, and the HSM is still alive. We have a terminal right there. You can look. The HSM is still kind of working. And yeah, you can do all sorts of things. You can, of course, debug. You can do experiments to reverse engineer stuff. And you can also dump the RAM, and the RAM, the SRAM, might contain some secrets. In our case, we did a little experiment. We tried to use the HSM module as an oracle. As you have seen before, you need the MAC, the message authentication code for the pin entry screen. The fake screen you've probably seen in the images, that was protected with such a MAC. And yeah, what you just do, the text string you want to have signed, you send it to the HSM with an obviously wrong MAC. That's the 4141, you know that. That's the wrong MAC. Doesn't matter which value that is. You just send it in, and then the blue stuff you see there is the text we want to have signed. And then, yeah, HSM happily compares the two and says, yeah, error, doesn't match, but no problem. We just halt the CPU via JTAG, dumps the RAM, we just look up the correct MAC, that's it then. Yeah, so much for the... Yeah, so much for the not so secure hardware security module, and now I go back to Carsten here.
Thanks. Yeah, good job. Yeah, just a bit of hardware hacking fun. This wasn't actually necessary for anything, but I think it is. I think it is important to know that this is possible to drive one key point home. So in this next chapter, we'll talk about what would actually need to change for these protocols to be secure. And one thing that cannot happen is for them to, again, bury some secret keys in some security module that they give hundreds of thousands of copies out. HSM and generally the idea of security by obscurity is broken, and we need a better approach here. What exactly do we need, though? Let's first revisit why these two protocols are so severely broken. As I said earlier, both of them have the issue of keys that are spread over a very large population of terminals, some of which may be secure, others are very insecure, like this ancient model that we are looking at here. The weakest link of the system then obviously determines the protection of these system-wide keys. These system-wide keys, they play out very differently in these two protocols here, though. Remember, in ZVT, there's a MAC, a message signature, which can actually be made very secure, even with a system-wide key, as long as you're using public key crypto. If only one person can sign messages, it's fine for everybody to have the same public key to verify the messages. Now, in this case, these terminals, I guess, when they were designed, they didn't hear about this great invention of asymmetric cryptography, and they're using symmetric signatures. So the signing key is distributed in 700-some thousand copies throughout Germany, amplifying the problem, and further, of course, amplifying by putting them in shitty HSMs that are, well, not just vulnerable to Dexter-style hacking, but to simple timing side-channel attacks. Right? On the Poseidon side of things, it's a little bit cleaner. We're not talking about cryptographic signatures here, but about authentication. And look at this as online banking, right? Each of these terminals is kind of like an online banking login to a merchant account. And if they're all using similar usernames and everybody uses the exact same password, cryptographic key in this case, this cannot possibly be secure. This cannot be fixed with public key crypto as long as everybody uses the same, in that case then digital certificate. This is not going to be secure either. In both these cases though, we need more individual keys as at least a midterm goal. Right? Fortunately, these protocols do have a provision to distribute a new key to a terminal, and this mechanism could be used to give a different key to every single terminal. So the road ahead should be clear. Some of the backend systems probably need to be adapted to work with individual keys per terminal. But it's already clear how we would get out of this mess. Give a different key to every single terminal. That's not going to save us in the long run when people start attacking the HSM chips again individually and then defrauding these merchants individually, but it would at least get rid of the possibility of very scalable fraud against tens of thousands, hundreds of thousands of merchants or consumers in this case. So the long-term goal is clear, better protocol. The midterm goal needs to be individual keys for each of these terminals, and a short-term goal could be things like switch off functionality that you don't actually need. How many shops do need to print SIM card top-ups? Certainly not every hotel and other establishments. How many stores do really need to refund through a card, right? Maybe you just do refund in cash and switch off that functionality too. Similarly, in ZVT, how many merchants actually want a terminal to be reconfigurable over a network with no confirmation whatsoever on the terminal? Perhaps a little, is this okay message, and somebody has to press a button would already fix a lot of this. So switch off what's not necessary and detect suspicious behavior. You can read faster than I can speak. You probably already went through this list, so I'll save you that. I promised a couple of times a more international perspective on this. Everything we discussed so far is focused on Germany and some neighboring countries, depending on which of these protocols it is. But we suspect very similar issues to exist in most other countries. The ZVT alternative that's used more internationally is called OPI, the Open Payment Initiative, and that is a much newer protocol that still does not have any encryption, though. Whoever sought in 2003 to specify a payment protocol and not to add in encryption, please send me an email. I'm curious. They did, however, do the what would seem smart thing of leaving out functionality that nobody needs anyway, and in fact, functionality that we are exploiting, like remote manageability of these terminals. The few instances of OPI we have found in Germany, however, they reintroduced that functionality as custom extensions. So apparently the terminal manufacturers, they find it very useful to have remote manageability, and if the protocol doesn't give it to them, they will introduce it as an extension. So exact same level of vulnerability in those few instances that we looked at. Of course, the research community at large is needed to verify this in different countries, and just with a little bit of Wireshark on the wire, you typically can. Similarly for Poseidon, as I said earlier, this is just one dialect of an ISO standard that originally came from MasterCard and Visa. So this is the suggested payment backend protocol pretty much worldwide, and we have seen encryption in some cases, not encryption in others. It doesn't matter, though. Remember, the attack actually goes through a full cycle of authentication. It establishes all keys well. It does all of this correctly, but everybody has the same key. What we're yet to see is a protocol by which you could exchange keys with these individual terminals, either put a key in or find which key it's using to establish individual keys. If anybody has more information on that, definitely look us up. But as far as we're informed, that there isn't a single instance where this ISO protocol actually is used with a meaningful key management protocol, and where this would at least have the foundation to be secure. But again, you, the international research community, over to you for looking at this in your countries. With that, to quickly conclude, two protocols used for payment in Germany, both of them to be considered insecure and very outdated. They both have the same root cause, something that fortunately can quickly be fixed, so there is time to improve the system before actual fraud hits. We as the research community should keep up the pressure for them to actually do that. But we as customers, we should not believe them anymore when they say, you must have given your PIN number to somebody, hence this fraudulent transaction on your account. There have been a number of cases like that in Germany this year, and I think it's time to show them who's really responsible for these security vulnerabilities and for leaving them open for so many years. Thank you very much.
We have 7 minutes for Q&A. Thanks to our speakers again for a only theoretical thread on the payment systems, of course, in a strictly lab environment, as the press wrote. Please leave quickly and quietly through the side doors now, so we have 5 minutes of Q&A. And Mike 2 starts.
How did you handle the question of disclosure? So did you do full disclosure, responsible disclosure? How much time did you give them?
We went through responsible disclosure, I guess. Meaning that we in detail tried to explain all of these attacks to an audience that we thought could fix this about a month ago, right?
And have you seen any reaction to that? Like, have they tried fixing it?
I'm sure somebody's working on a fix, but nobody would tell me. Yeah.
Okay, and we have one question from the internet.
So can you say if there's an easy fix, like just flashing a new firmware into all terminals?
Yeah.
Like flashing firmware to all terminals?
It's an easy fix.
Yeah, you have shown the fixes. These are the difference between this research and the research done 3 years before is that these are now flaws in the protocol. So these need new protocols, new versions, and new yeah. That's it. So these are no implementation flaws right now.
But would you have to scrap all terminals and buy or construct new ones?
I think the honest answer is that criminals are slow too. So this will have to be a somewhat longer journey in which we first replace the system-wide keys by individual keys. That would already help tremendously in making it less attractive to do these types of attacks. But then in the meantime, work on better protocols so we don't keep finding ourselves in a situation where it will take years to fix protocols. Well, let's use those years ahead of us to do that.
Thanks.
Okay, microphone 8, please.
How many tries did it take to pull the keys out of the terminal? How many boxes do you have to blow?
3 or so.
Yeah.
I mean, the first one was surprisingly an immediate success. We managed to restore the SRAM without destroying it. The second one we broke immediately, and the third one had issues after it, but we managed to fix it.
So you didn't wipe any keys bypassing the mesh?
Didn't understand acoustically,
So,
sorry.
When you were bypassing the mesh, you got that the first try?
Yeah, I tried it the first time.
Wow.
So like, I think a bit of preparation and then one hour of actual work.
Well, you destroyed the first terminal for just looking at how it's built, right?
Yeah. We knew how it was made up because we took a few apart before, of course.
Yeah.
But not with the intention to do that just because they're broke, and then we took it apart to look up, to read out the flash. This bug bonded thingy, that was one of the very first ones that broke.
Okay, microphone 7, please.
Would you please briefly describe what will do the terminal in case if some transaction wasn't processed by the bank? What kind of information it will store in memory and how long?
It will store where?
I don't think the terminal stores anything. It's pretty much stateless. It receives a command looks up its configuration, like terminal ID, it pushes it down to HSM to get signed or get a PIN number, pushes it over Poseidon, and forgets all about that transaction.
So it's not trying to resend the transaction again somehow later?
Good question.
So this is not part of the attacks we have demonstrated, but what happens is that normally you will do an end-of-day command or a Kassenschnitt in Germany, where all the transactions that have been accumulated throughout the day will be sent to the payment processor, and this is the exact moment where all these transactions are then sent by the transaction processor to the bank. So at this point, for example, no reversal is anymore possible. Reversal, like reverse one purchase on the same day, because then the bank has already the information. And then no information is stored anymore on the terminal if this one was successful.
Okay, thank you.
And one more remote question, please.
So is the communication that you used in the man-in-the-middle attacks also susceptible to replay attacks? Can you just do it without a terminal if you recorded the conversation between terminal and processing server?
Sure, we can inject messages, ZVT messages. Most of them are not actually protected with a MAC. For instance, you can query a MAC stripe with no protection. However, there needs to be somebody in the store who expects you to do that, right? So it's convenient to just be man in the middle in an actual transaction because you know there's somebody waiting for you to stick in the card. There's a customer waiting to stick in their card. So you wouldn't get that from just sending random messages. There's just nobody there with a card.
Okay, and one last question, a quick question from microphone 1.
Yes, you said there's the possibility to give an individual key to each terminal. So you have an identical terminal to another one. So if the payment processor sends out individual keys to each terminal and there are two of one terminal, what will happen?
Yeah, good question. So if the fraudsters first take over all the terminals and you then send individual keys, that's not going to help. You've got to be ahead of the bad guys here. Right? Yeah.
Okay, thanks again to Dexter, Fabian, and Carsten.